So this is revision material of the section that's basically under the emission of light, about pages 25 to 27, somewhere thereabouts in your distance learning notes. I just wanted to kind of discuss some of these concepts, and the equations that are held in this this section, this slideshow, are the only ones that you will need to learn. Any other equation you'll be given. So here I'm going to talk about lifetimes rate and quantum yields. Now, starting off with the natural lifetime. The natural lifetime is essentially if we have an excited state and it only decays via emission, then the natural lifetime is the length of time it would take for the concentration of the excited state to drop to 1 over E, or about 0.37 of the initial concentration. It's not a concept that we use a lot, except to say that it links our rate constant for loss of the excited state to something that we actually can measure a little bit more directly, which is the lifetime. So you can see I've got these two just simple first order equations. This is just a first order decay. In the second of the two here, I have a rate constant, a traditional kind of rate constant, e to the minus kt. In the top one, I have this lifetime, which is just 1 over the rate constant. This use of the tau 0 or the kf 0, this is to say that it's the natural lifetime or the natural rate constant for this process. In other words, all of the light is decaying by fluorescence. So if all of the light is decaying by fluorescence, then my fluorescence quantum yield is 1, because my fluorescence quantum yield is my measure of what proportion of the excited state decays by each different pathway. And more formally, here I have my definition of my quantum yield as being the rate constant for the fluorescence process divided by the sum of all of the rate constants. But if I've only got fluorescence, it's just divided by the rate constant for fluorescence. So you can see it's just 1. So just to recap that, the lifetime is referred to as the natural lifetime if I'm only looking at a process of fluorescence, and that my link between this natural lifetime and my rate constant is just a reciprocal relationship. 1 over kf is equal to the natural lifetime tau 0. So now if I introduce other techniques, other methods of decaying from my excited state. So I've got this orange one, this is my emission, but now I'm also saying that I can have internal conversion, so just this vibrational relaxation, or I can have an intersystem crossing, which I've referred to here as ST, so singlet to triplet intersystem crossing. So now I've introduced other mechanisms of decaying from my first excited state. So now my quantum yield for emission drops because it's no longer just the kf portion. I'm now introducing intersystem crossing and internal conversion into the mix as well. And so we can see this if I look instead at how the concentration of excited state changes. As I introduce these new components, I can see that my lifetime is decreasing, my decay happens more rapidly because I'm introducing more and more and more components. I'm assuming here that just my natural lifetime is the same and I'm just introducing other components. So here we have what we refer to as a lifetime. And my lifetime in this case is just the same amount of, I have to drop to this 0.37 of my initial concentration, but it's no longer the natural lifetime because I've got other methods of coming in. So just to summarize all of that in terms of equations for quantum yield, we can see that my quantum yield equations whilst formally I can have it over the rate constant, I can also think of it in terms of just this lifetime of this singlet state, because the lifetime of the singlet state, as we can see, is made up of 1 over the rate constants for all of the different processes. I hope this helps. There'll be others appearing.